So we've talked about functions, and we probably all know a function is a relation in which each input has exactly one output. Okay, that's fine, that's great. And why do we care about functions? Well, many things in the world, you just have one input and one output. If you throw a marker, right, it's only at one place every time interval. If you have money in your account, you don't have two different amounts of money in the account at the same time. It's just one amount. And there's lots of other things we could think about. But let's just look at one simple function. Let's say y equals 2 over x. And let's really just try and figure out what we're dealing with here. Is it a function? What does it look like? So there's lots of different ways to analyze functions, and a lot of times you're just given this. Boom, here's a relation. Is it a function? Is it not a function? I don't know. So what we want to make sure that we can do with these equations is represent them in multiple ways, because representing functions in multiple ways is going to help us understand what's even going on with these functions, and whether they're even functions at all, and whether we care about them. Who knows? So y equals 2 over x. So one thing I just want to show you initially is that it's good to think about functions. So here's representation number 1. Algebraic representation. Okay. It's good to think about functions in terms of them being a machine. So this is just going to be sort of like, I don't know, machine representation. So here's how it works. Let's build our little function machine here. It looks like this. Very cool. Cool, cool, cool. Great. Yoink, yoink. Love it. Okay. So this is our function machine, which we are going to call, let's rename this thing f of x. So let's call it f of x instead of y. And so this is now my f machine. Okay, great. So if I plug 2 into this function, yoink, it goes in here. 2 gets plugged into this. I get 2 over 2. Out comes 1. Great. If I plug pi into this function, yoink, what comes out? Well, 2 over pi. Yoink, 2 over pi. If I plug negative 1 into this function, here we go, plug into the function machine, f, which is, by the way, f of x equals 2 over x. Out comes 2 over negative 1, which is negative 2. If I plug 0 into this function, I get 2 over 0, and that, my friends, is undefined. Okay? Dividing by 0, that's like asking the question, how long does it take to fill up a bucket of size 2 with nothing? What? That doesn't really make sense. It's kind of like, well, infinite amount of time, sort of, right? So that's undefined. So what that tells me is that this, by the way, is not part of the domain because it gave me a problem, okay? But everything else it looks like is fine. I could probably even plug in like 0.2, and if I plug in 0.2 into 2 over x, I get 2 over 0.2, and 0.2 goes into 2 like 10 times, so I think that that's 10. So I can get lots of values, negative values, positive values, yada yada. If I plugged in 1 million, I can do that. That's cool. So I can do what I want because I'm an adult. As long as it doesn't hurt other people, of course. I get 2 over 1 million, which is tiny. But it's still a legitimate number. It's still a small positive number. Great. So this is how functions work. And by the way, over here we have the domain. These are the things we plug in. And over here we have the range. These are the things that we get out. So that's how this works. Domain gets sent to range. And so I think it's good to think of a function as, whoop, take this thing, plug it into a machine, out comes something, or maybe out comes an error in which case you need to say that's probably not a part of the domain. Okay, another way that's really nice to look at functions is through a table. So let's call this x. This is x, and let's call this f of x. Okay, fine. So we can choose whatever we want to plug in. Let's say we wanted to plug in these same values. 2, 0.2, pi, -1, and 1 million. Normally when you're making a table, a good place to start is with the values -2, -1, 0, 1, and 2. These are like classic values that are usually pretty easy to plug into functions, but I'm just plugging in some random things. So then my f of x values would be 2 over 2, 2 over 0.2, 2 over pi, 2 over -1, and 2 over 1 million. And, you know, that's 1. This is 10. This is like, you know, some decimal number. This is -2, and this is tiny. It's some tiny number. So anyways, we can represent a function in a table, and then we can start to look at, okay, what it would look like. Okay, finally, we would like to, maybe not finally, but we would definitely like to be able to look at a graph. So this is really, really important. There are really two ways to graph things. One is to just plug in a bunch of numbers, plot all those points, and then see what it looks like. That is a fail-safe method. You should be able to plot the point 2, 1. 2, 1. There it is, right there. You should be able to plot the point 0.2, 10. 0.2 is tiny here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 0.2, 10 is right there-ish. You should be able to plot the point -1, -2. Here's -1, here's -2. No problem. Here is the point 1 million. Okay, maybe not that point. But anyways, I know that if I plug in 1 million, I'm going to get a tiny number. So what would happen if I plugged in, say, 10? Well, I would get 2 over 10, and that's 1/5. So I know if I plug in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I get 1/5. But still, if I don't know the general shape of this function, I'm going to have to do a lot more points, and I don't really want to do a lot more points. I'm already kind of bored with the points, to be honest. So it is really helpful to look at this and know the shape of this graph is this. This is why we actually care about, okay, I just want to know what is the shape of this graph. I already know it looks like this because any function that is some value k over x looks like this. So initially I said, okay, the fail-safe way is to just plug in points and graph those points. And you need to be able to do that. I think it's always a good thing to have a few points. And in fact, I might want to put a couple more points on here before I sketch. But we also want to know the general shapes of things and know how multiplying, adding, subtracting change the function so that we can generalize and get a very quick understanding of what it looks like and then get more specific if we need to. So I'll plug in just a couple more points. If I plug in -2, I'm going to get -1. If I plug in, say, 1/2, I'm going to get -1/2, I'm going to get -4. If I plug in 1/2, I'm going to get 4. If I plug in let's say -4, I'm going to get -1/2. Then, knowing the general shape of this, I can sketch a graph that looks like this. It's got some asymptotes. It has an asymptote, a line the function approaches at x equals 0. By the way, that's the y-axis. And it has an asymptote at y equals 0. By the way, that is the x-axis. That's not how you spell axis, but it's pretty close, to be honest. Okay, so now I can see some more things about this. Graphically, this might help me see, what the domain and range is. I can look at this and see some things about the domain and range, like domain, positive number, decimal number, irrational number, negative number, huge number, 10. Fine, whatever, 10. 10 is just its own thing. It's just its own friend, its own pal, whatever. 0. Nope. Cannot plug 0 in because then I'd have 2 over 0. So that is why it's not in the domain. And I can see here that this number, this x value, which is x equals 0, does not exist. So the domain here would be x does not equal 0, or I could write negative infinity to 0, 0 to infinity. And the range, same thing. Range is always harder to find here because I see positive numbers, I see negative numbers, I see tiny numbers, I see irrational numbers, I see fractional numbers, but what I don't see is 0. And no matter what I plug in here, even if it's huge, I'm not going to get 0. And that's why the function does not cross this line. So my range here would be y does not equal 0, or alternatively, negative infinity to 0, union 0 to infinity. So that's one example of thinking about a function algebraically in terms of sort of machine representation, inputs, outputs, in terms of a table, and in terms of a graph, and then looking at domain and range. So I hope that's helpful. Okay. See you later.